So we will talk about map and MMS estimators. I will explain what these terms mean as we go along. The whole point is we start with a unknown parameter. Theta is unknown, but it is a random parameter. So essentially we are going to talk about a random parameter estimation. So then it has some density function f theta theta. So this is where we start. It has we don't know what its value is, but from previous knowledge, it has an a priori PDF. So either through model or someone told us whatever. So this is where we start. Then we collect some relevant data, x1, x2, etc., xn. Of course, the data is random, so they have their own density function also. And of course, if the data is independent, this becomes the product of the density functions, etc. And so the implicit in all this is that not only the data has a joint density function, the joint density function, and in fact, if you take the data and the unknown random variable, their joint density function also is something well defined. In other words, if these two are independent, then obviously this is waste of time using this data to say something about theta. So implicit in all this is the assumption that this joint density function is also well defined, and we may know it or we may not know. So in any case, the question is, given all this, how do you get a good estimator for theta? Remember, that's our goal, to figure out theta from the data. So assuming the experiment, etc., has been done properly, how do we proceed? So given all this information, we have the a priori PDF, and we have the joint description between the data and the parameter through this through the joint PDF. So what we mean by a good estimator? Obviously, the first thing that comes to mind is this should be as good as this, whatever is its current value. In other words, the difference, the error, could be used to move forward. So if you define the error to be theta minus theta hat x, we can naturally say we want to minimize this error. But remember, if you look at that expression above, everything is random here. This is a random variable. This is random because data is random. So we should speak about minimizing the error in some average, statistically average sense, or mean square error minimization. So this leads us to the notion of MMSE estimator, minimize mean square error estimator. So we can write it this way: sigma theta, we need to minimize over theta hat expected value of. So this is now mean square error. Error is here. So this, of course, I can remember the random variables x and theta. So this, of course, I can write it as theta minus theta hat x squared f of x1, x2, etc., xn, and the theta dx1, etc., dxn, d theta. Now, there are too many things going on here. So if you want, we can write this as degree of difficulties. We can write it in terms of a conditional density function, so that we deal with one difficulty at a time. So that this expression now reads, if you want, so where the limits of integration are wherever they are, I'm just going to put in general as minus infinity to plus infinity. So suppose I write it this way. So what I have done is computing this complex quantity. I did it in two steps. In the internal, in one step, I am computing the conditional error based on this conditional distribution, and then I average it out over the data. So I'm going to make this notation of theta given x. And this is, notice that this is where theta hat comes in. So all the minimization need to be done here. Yeah, that's where the theta hat comes in. So I'm going to pick up that term and see what happens. So sigma squared theta is sigma squared theta given x f x dx. So let's concentrate here. Sigma squared theta given x is integral theta minus theta hat f theta given x1 etc. xn. This is just the data d theta. This need to be minimized to minimize this. So I'm going to take the derivative. Remember here, if you look at it, these data are frozen or given. So consequently, in this case, because it is conditioned on the data, this is just a unknown, not a random variable anymore. So we can take the derivative with respect to that theta hat. And that gives us, taking the derivative inside, that gives us a derivative with respect to theta hat. So 2 theta minus theta hat x multiplied by minus 1 density function. There is no theta hat here. So just the density function d theta equal to 0. So if I write it as two integrals, this gives us integral theta hat x multiplied by theta given x d theta equals integral theta f theta given x1 etc. xn d theta. But notice this is a constant that goes outside, and whatever is remaining area under, so the integral comes here, but the area under any density function is 1. So the left side is just theta hat, and the right side is the conditional mean of theta given x. So we get this classic expression. The best estimator, which is the MMSE estimator, which is what we are dealing with now, is the conditional mean of the unknown parameter given the data. So I'm going to do a quick example to show the dynamics of working this out. So this is one way to get an estimator. So let's look at this. I just made up a problem. Let's say f of theta x is given by k of, which I will take some x plus theta in this region. So this line is of, this is x, this is theta. So this is 1, 1. Then this line is x plus theta equal to 1. So we want the condition, the MMSE estimator. That's theta f of theta given x d theta given x. So if x is given to be some value, look at this problem. I purposely made it this way. If x is given, then this is theta. Theta doesn't go up to 1. If x is given to be x, theta only goes up to from here. Theta will be 1 minus x. So the upper limit is 1 minus x. But we need to deal with this conditional density function, which is not given. But that's the joint density function, which is given, divided by the marginal of x. So we need to find the marginal density function of x. So that's going to be the joint density function of theta and x, integrate out theta. But x is given to be some value. So again, theta goes up to 1 minus x. So theta goes from 0 to 1 minus x. So this is k multiplied by x plus theta, 0 to 1 minus x. So this is k multiplied by x theta plus theta squared by 2, 0 to 1 minus x. So this is k multiplied by 1 minus x here, 2x plus 1 minus 2x plus 1 minus x by 2. So this is 1 plus x. So this is k by 2, 1 minus x squared. X goes between 0 and 1. So we have this. We can substitute it here. So the numerator is k multiplied by x plus theta. Denominator is k by 2 multiplied by 1 minus x squared. So the whole thing becomes 2 multiplied by x plus theta divided by 1 minus x squared. The variable is theta, but theta goes between 0 and 1 minus x. So this is the answer we need to substitute here, which I'm going to do in the next slide. So theta hat MMSE is 0 to 1 minus x integral theta multiplied by the conditional density function of x given theta. So that's 0 to 1 minus x theta. We just found the conditional density function to be x plus theta over 1 minus x squared d theta. So basically, we just need to compute this integral. So this is 2 over 1 minus x squared goes outside. Integral is 2. Integral, I'll write one more step. So this is x theta plus theta squared dx. So that's going to be 2 over 1 minus x squared. So from here, x theta squared by 2 plus theta cubed by 3, 0 to 1 minus x. So when I put theta equal to 1 minus x, I can pull out 1 minus x twice outside. And I have 2 here. Here I have 1 minus x, 1 plus x. Then what remains here is theta squared, I mean 1 minus x squared I pulled out. So we have x by 2 plus 1 minus x by 3. So if I simplify just this becomes 3x plus 2 minus 2x by 2, which is 2 plus x by 3x plus 2 minus 2x. So 2 plus x by 6. 2 and 3 2 cancels. So this becomes, and here 1 minus x squared and 1 term cancels. So you have 1 minus x divided by 1 plus x multiplied. There's a 3 here. And in the numerator, there is a 2 plus x. So this whole thing turns out to be 1 minus x multiplied by 2 plus x divided by 3 multiplied by 1 plus x. X could be whatever is the value of x. So this is the conditional, this is the MMSE estimator for this problem given once we make a measurement on x. I wanted to show that I picked up some problems so that you can see that MMSE estimator may not be pleasant, certainly may not be linear. As you can see, it's a non-linear estimator, could be a non-linear estimator. And more importantly, to do this, you need the joint density function between the unknown and the data. And that may or may not be available. But right now, we are assuming it's available. So that's one estimator. And the map estimator, the reason I did the MMSE first is the other estimator, map estimator. So what is map? I'll explain to you. We can bring, so one way to see the MMSE is we used on error, we used a quadratic function, mean squared error, as the error function, as the criteria for minimizing. So instead of this, suppose we use some other criterion. In other words, let's say I use a function like this. So here the function was quadratic, right? Phi epsilon squared versus epsilon. That gave rise to MMSE. But suppose I say this is like an all or nothing function. If the error is very small, there is no penalty. That's what it says. If the error is large, the penalty is 1. So phi of epsilon is 0 if error is less than delta, and it is 1 otherwise. I think this is known as the all or nothing function, criterion. So this is used in radar mainly. In other words, if the error is very small, you don't have to worry. If the error is large, you're dead. So that's you pay a big penalty beyond a certain stage. So let's just do the MMSE using this. So again, minimization of using this criteria. So the question is, what is the best estimator? So here we remember error is of course theta minus theta hat. So everything is random here, except we are going to minimize this phi function, not epsilon squared as we did earlier. Minimization, and of course the minimization is going to be on phi of theta minus theta hat x. So the minimization is still on theta hat. So how do you proceed now? So if you write this, you can see that this is the same as, so let's write down, it says a double integral phi e, phi epsilon, and then all the parameters involved, x1, etc., xn, and theta, dx1, etc., xn, d theta. But this has got this nature, so I'm just going to draw here again. So you can see this function is only effective in everywhere except in this region. So that one way to write this function also is the all one function minus, you can write it as this function. So I'm rewriting this function as 1 minus this. So here, of course, so when you integrate on a density function using all 1, it's of course the area under this double integration is 1. So I hope you see that if I make a notation here, let me call this sigma squared 1, whatever that 1 is. So sigma squared 1 is minimization of over theta hat 1 minus the double integral on this function. So this function is, if you look at this function, it actually goes non-zero only from minus delta to delta. So this function is minus delta to delta, and you have the variables x1, etc., xn, and theta, etc. So again, I'm going to write this as before on the conditional density function, theta given x, and f of theta, etc. So this is going to be minimization is on this term on theta hat. Remember, theta hat is an unknown function here, and this is going to be again the immediate thing that the quantity that's of significance is theta given x1, etc., xn. So the theta hat is here because theta hat is theta minus some unknown function of x, but the density function is precisely this multiplied by f of x dx. So you can see if you want to minimize this, that means on this density function, let me plot this density function, the inside density function. So this is the density function which you see here, theta given x1, x2, etc., xn. We want this quantity to be minimized. That means whatever is this within this small interval. So remember, this is already a tiny interval, minus delta to delta, around maybe actually I should write. Remember the Okay, I missed a few steps. The epsilon is theta minus theta hat. So if I translate this in terms of theta, this will be from theta hat minus delta to theta plus delta. So what I'm trying to say, here it should be theta hat minus delta to theta hat plus delta, because epsilon is theta minus theta hat, and epsilon goes between minus delta and delta, which is the same as saying that theta should be theta range should be between minus theta hat minus delta to theta hat plus delta. So all I need to do is just to make sure that these limits are theta hat to. So the question is, what is the best value of? So we want to minimize this. That's the same as saying that we want this inner integral to be maximized. So, so if the inner integral is like this, it obviously will be, if you remember here we have the freedom to choose theta to be wherever you want, theta hat to be wherever you want. So obviously we should choose theta hat where this integral peaks. But if you look at this, this curve peaks. This curve corresponds to the a posteriori PDF. So this is the a posteriori is after measuring, after what? After measuring the data. So if you look at the problem, we started with some prior knowledge on theta, and then we came over to this. So we started with something like this. We have some prior knowledge, then we collected the data. So the data, they have a joint distribution. From there you have a posterior distribution, which is the posteriori PDF of theta. And we need the maximum of that. So if you coin this word maximum of AP, that gives you the MAP acronym, MAP estimator. So this is the MAP estimator. Obviously, it's a function of data, so I'm going to put the subscript of this. So actually, technically the minus is here. So the minimization is minimization with the minus sign is the same as the maximization of the term without the minus sign. So that's so remember, you're integrating on a tiny region. Minus delta to theta hat minus delta to theta hat plus delta. So you want this integral to be maximum. So if you take anywhere else, this will be less than this value. So this is the MAP estimate. So what's the moral? Moral of the story is you have F theta, a priori PDF, and then you have the data, x1, etc., xn. From that you compute the a posteriori PDF of theta and go for its maximum. That's the MAP estimator. So let me do a few problems. So MAP estimator is at the maximum of f of theta given x1, x2, x3, etc., xn. Or we could say maximum. So the maximum is on the theta hat, maximum of logarithm of the, because the f and log f are monotonic increasing. So we could also do the logarithm of f of theta given x. But this a posteriori PDF, you can write using the Bayes relation in this manner. Remember, here x is x1, x2, etc., xn. So if you take the logarithm of the a posteriori PDF, that's the same as the natural logarithm of x1 theta plus log of theta minus log of fx. To find the maximum, we can take the derivative with respect to theta. So here the derivative with respect to theta. And then we equate it to 0. So d log of f of theta given x by d theta at theta equal to theta hat map, we can also write in terms of these expressions. There is no theta here, so this is d by d theta of log of f of x given theta plus d by d theta of log f theta. And you put theta equal to theta hat map and equate this to 0. So this is the expression we'll use. Either this expression directly, if we can't compute this, we'll compute this, these two terms. Two terms, remember. There were actually three terms, but the third term has no theta dependency, just the density function of x. And which has been extracted out of the theta has been extracted out of the denominator term here. So when you take the derivative, you only have these two terms. So this is what I'm going to use to finally do a few examples. So let me start with some classic problems. Let's say observations are of this form. This is unknown parameter, but random. Ni are, let's say, noise. Let's say each of them are zero mean and some variance sigma n squared, Gaussian, right? Normal random normal noise, and independent identically distributed. And theta, I'm also going to assume is that some so theta may be some temperature, right? Some mean value from whatever, some, let's say, mu, and some variance theta, this is sigma mu squared. It could be zero here, but let's take this problem. So I'll use this expression. So we need f of x given theta. Remember, if you look at xi, so you have, let's say, I equal to 1 through n observations. So if first we are looking at x1, etc., xn given theta. So if a theta is given, then this is a constant, unknown constant given. Then the randomness is, I can argue like the randomness is only on ni. Ni's are Gaussian, zero mean. So if I add theta, this becomes, mean becomes theta and same variance. So first of all, my conclusion is each of the xi's are, not all of them, each of the xi's are of this form. And they're all independent because ni's are independent, I equal to 1 through n. So this density function is, and so the joint density function of all of them given theta is the product of the marginals of xi given theta. So that's going to be 1 over 2 pi sigma n squared to the power, let's say, n observations, n by 2. This is just noise. I'm going to use e raised to minus sigma xi minus mu the whole squared over minus theta, because theta is over 2 sigma n squared. So that's this one. And the second term is given to be, and theta is given to be f theta. Theta is Gaussian also. That's 1 over 2 pi sigma mu squared e raised to minus theta minus mu the whole squared over 2 mu sigma mu squared. All right, so if I substitute all this into this expression, I'm going to compute this quantity, log of theta given x is going to be log of f of x given theta plus log of, these two terms are all that really matters. So I need to take the derivative of, so when I take the logarithm of this, notice that I'm only going to put the logarithm of this constant, which is not a function of theta. So I'm going to put some constant minus xi minus theta the whole squared over 2 sigma n squared from here. And same thing here, you have a constant. So let me absorb all that constants here. Then you have minus theta minus mu the whole squared over 2 sigma mu squared. And technically there is one more term, log of f of x plus log of f of x. But in the next step, when I take the derivative with respect to theta, that none of these constants, etc. matter. But I'll write it like this. So I'm going to do it here. The derivative is going to be, remember there's a minus here. So this is going to be sigma xi minus theta. Then the derivative, 2 cancel. So you have sigma n squared. There's a minus here. This minus will come. So this will stay as it is. And here you have minus theta minus mu. And the derivative is with respect to theta. 2 goes away. So you have sigma mu squared equal to 0. Theta equal to theta hat map. So you just have to solve this for theta. So you can see from here you get theta multiplied by, remember this summation is here. So this is n over sigma n squared plus 1 over sigma mu squared multiplied by theta hat map equal to sigma xi over sigma n squared. This is the data. And there is one more term here, mu over sigma mu squared. So this is just a constant. So you can solve for theta hat map. So basically theta hat map turns out to be so notice that this will become let me try to do this as sigma mu squared plus sigma n squared. And when I take the so this will come here, and this is some sigma mu squared sigma xi I equal to 1 through n plus sigma n squared mu. So anyway, it's a linear function of data. That's what it turns out to be in this case. So that's one example. So this is the map estimator for the parameter theta, which is contaminated by Gaussian noise. And of course, if the parameter had 0 mean, then this term wouldn't be there. It would be just this. And as a final example, let me make up a problem on let's say so here the estimator turned out to be linear. Let me change the prior in the same problem. So in other words, once again, the problem is xi's or xi's of the form theta plus ni. So ni's are Gaussian, let's say with 0 mean, some variance sigma n squared. And theta is has some PD of f theta. I'm going to write it down. Let's say this is theta over sigma squared. Say sigma 0 squared. So those of you remember, this is like a Rayleigh PDF. So let's just see the dynamics here, what turns out to be. So I'll do this quickly. We need log of f of theta given x equal to log of f x given theta plus log of f of theta. F of theta is here. So let's find out x given theta. X given theta is as before. Let's say you have capital N observations. So that's exactly the previous term. So I'm just going to copy from there. Minus sigma xi minus theta the whole squared over 2 sigma n squared plus the logarithm of this term. So that's going to be plus log of theta minus log sigma naught squared, which doesn't really matter, minus theta squared over 2 sigma naught squared. So we need to take the derivative of this with respect to theta. So I'll complete this in the next page. So that's going to be, so the derivative of log of f theta given x is going to be sigma xi minus theta over 2 cancel sigma n squared. This multiplied by minus 1, so you get this minus 1 goes away, plus 1 over theta minus 2 theta, 2 cancel, so theta over sigma naught squared. This should be equal to 0. So assuming theta is not, so if you expand this, this comes out to be sigma xi over sigma n squared minus n theta over sigma n squared. So there's two terms of theta. So minus 1 over sigma naught squared multiplied by theta plus 1 over theta. Theta equal to theta hat map equal to 0. So my whole point is, you can see it's a nonlinear equation. So if theta is not 0, I can multiply by throughout by theta and get a quadratic equation. So this gives you n over sigma n squared plus 1 over sigma 0 squared multiplied by theta hat squared. So you need to solve this equation. Minus sigma I over sigma n squared multiplied by theta hat map minus 1 equal to 0. So it's a quadratic equation. So the solution is going to be theta hat map is nonlinear here. And once you have an estimator, of course, you can try to find out its variance and this and that. But when you have nonlinear, so whole point is, unless it is a real nice Gaussian case, the depending on the a priori PDF, the actual estimator term may turn out to be non-linear, and so you just have to deal with it. And finally, before we close this, one final remark I want to say is that we can also use this for learning. So, in other words, improve upon our ignorance. So this is your a priori PDF of theta. There's very little is known about theta. Then you collect the data, and that may tell us a little more about theta, so that you have the a posteriori PDF given data. So this was data X, and so this tells most likely this is a this is the map estimator wherever this PDF peaks. This is the a posteriori PDF for theta. Now, if you collect more data, then we should not go here. We should take this as the starting point. This as the starting point. Let's say we collect more data Y, then we can update this using further conditioned on Y, etc. So that's what I meant by learning. So you go from here to update the density function of theta, but given Y, and so on. So this is still theta. So this may have more information, etc. So this is sequential updating, which is learned from the prior data, previous data. Thank you.